Greetings, everyone. I am UDAY SHARMA of the EEE Department of Institute of Aeronautical Engineering. Today, I am going to discuss about hydropower generation and instrumentation measurement and how to measure the efficiency of a hydropower plant. There are many ways of power generation. One of them is hydropower generation. Hydropower is one of the major ways of power generation over the grid. Like if you compare the dam hydropower generation in China, it generates 22,000 megawatt at a time. Hydropower generation is also a form of renewable generating the power. The efficiency of hydropower plant is also one of the highest when we compare to the methods of generation. It is about 90%. When you also consider the advanced methods like pumped storage plants, it is even more efficient. Let us discuss how the power is generated through the hydropower generation. Hydropower plants are placed over the water reservoirs. When the water from a height are channeled through the pipes and directed towards the turbine starts to rotate. Like if you consider this as a water reservoir, when the water starts to flow, this is the penstock. You consider the turbine is placed at the bottom of the penstock. The water flows with a force and rotates the turbine. When the turbine is rotated, the power is generated. The turbine is connected to the generator to convert the mechanical energy obtained from the turbine into electrical energy. When this power, when the turbine is rotated, we obtain mechanical energy. This through alternator or generator converted to electrical energy. Then the generator is connected to the form of transformer, which we generate is stepped up and sent us through the transmission systems or transmission lines. Suppose when the output of this generator, suppose let it be 11 kV, the transformer updates it to 1750 kV or etc. The water which leaves the turbine are often combined into the river, or in the case of pumped storage plants, they are again pumped back to the water reservoir. Let us discuss this diagram of the hydropower plant. Here, this is the reservoir where the water is stored before entering into the hydropower electric dam. Here, this is the intake gate. This is the penstock or the pipe we discussed earlier. At the end of the penstock, we connect a turbine. To the turbine, from when the intake gates are released, the water flows through the penstock into the turbine. The turbine starts to rotate due to the force of the water. Then, when this rotates, mechanical energy is generated. This mechanical energy is converted into electrical energy through the generator. And from the powerhouse, the generated energy is transmitted to transformer, and then again through the transmission lines, it is distributed. The water exits from the turbine towards the penstock and mixes into the rivers. When we consider a pumped storage plant, pump is placed at this part of the plant, lower reservoir, and is again pumped back when the demand is low to the higher reservoir. Efficiency management of a hydropower plant. To produce electricity, hydropower plants convert the potential and kinetic energies of the water to electrical energy. The amount of energy generated depends on the head of the power plant. Like if the head is high, it creates greater force. If the head is low, it creates less force. The amount of energy generated depends on the head of the power plant. The water discharge, like the size of the penstock. If penstock is high, the water comes with a great force. Penstock is low, the force changes or varies, depends on the size of this penstock. And the efficiency of the machines, like how efficiently the turbine works, etc. There are many compelling reasons for measuring the efficiency of hydroelectric turbine generator units. The first is to verify whether the contractual performance guarantees are being met. Like if the manufacturers gives us a machinery with a separate contract, like it generates this amount of energy, or this transmits this amount of, this generates this amount of energy. We have to verify. So we need to do the efficiency calculations of the transformers or generators. The second is to help verify the return on investment after a unit is refurbished or replaced. Like if we replace a generator, a small generator with a bigger generator or larger generator, we need to calculate the return on investment. How much days it would take, or how much time it would take to get our investment back with the help of this output of this investment of this machinery. The third is to improve power plant operation based on the information obtained during the tests. Suppose we are getting an output of 10 kVA when you use one separate of size of a transformer or generator, and if we replace a generator with a bigger unit, what is the output we need to get? Like if the efficiency of the power plant is going to increase or not. We need to calculate these things when we calculate the efficiency management. The sizes of the parameters can be varied to get efficiencies. Like the head can be varied to get a lower or higher efficiency, as discussed earlier. Based on the heights of the head, efficiency varies. So the engineers have to plan ahead to find an optimal and constant efficiency all the time. The efficiency of the power plant should be always same. To determine the efficiency of any turbine generator unit, two parameters are needed. The turbine input mechanical energy, which is determined from water flow and pressure, and the generator electric output power, where the unit efficiency is generator output power by turbine input power, and the turbine efficiency which we get is the turbine output power by turbine input power. Let us discuss this briefly. For better accuracy, the measurement technique used for the output power measurement is done using the 3-watt meter method, when the neutral of the generator is grounded through the reactance. The generator output is measured by the means of 3 voltage transformers and 3 current transformers and a 3-phase precision electric wattmeter, where the power total is equals to power of each phase PA, PB, and PC. The voltage of each phase is measured using portable calibrated voltage transformers, which provide a high level of accuracy since they can be calibrated before and after the test. Output power measurement. To calculate the efficiency of anything, we need to first measure the output power. To obtain the turbine output power, the generator losses are added to the corrected generator electrical output power for the specific operating conditions. The generator losses are considered are the core losses, bearing losses, brush friction losses, tail load losses, rotor winding losses, stator winding losses, and ventilation losses. These are the losses which we need to consider during the output power calculations or measurement. Experience shows that there is a 5% accuracy of the generator loss measurements. After the unit and the turbine efficiency measurements, the segregated generator losses are calculated for each phase operating condition. There is a 5% accuracy difference when we consider these losses along with the calculation of the efficiency management. Input power measurement. Turbine input power depends on physical properties and the head of the water. However, it is also proportional to the water discharge, as we discussed earlier. The flow of water, the rate of flow of water, the rate of flow of water along the penstock. However, it is also proportional to the discharge passing through the turbine. 4 main methods can be used to measure water discharge, which is often the most demanding part of the efficiency measurement. They are current meters, caustic meters, the pressure time method, and the thermodynamic method. Let us discuss few of them. As we can see, the current meters. With the measurements of velocity at multiple points in a cross section of the conduct, it is possible to obtain velocity profile. To have an accurate profile, it is important to cover the cross section with more current meters in the boundary layers where the flow is most turbulent or irregular. The discharge is calculated by integrating the velocity over the area of conduit cross section. Measurements are commonly taken with the current meters installed on a fixed frame in a section of the penstock. As we can see here, the current meters are attached to a fixed frame over the penstock. To calculate the velocity, we have covered the major part of this turbine. We have covered the major cross-sectional area to say of the penstock. Acoustic measurements. The transit line acoustic methods of discharge measurements use the difference in travel time of the acoustic pulses transmitted downstream versus upstream on a given path crossing the conduit to determine the average velocity of the water along that path. To do this, the propagation speed of the acoustic signal is added vectorially to the flow velocity. The discharge is computed by integrating the velocity of multiple paths, assuming a fully developed velocity profile. On the other hand, the transit time method has the advantage of being simple and often easy to install. The acoustic flow meter communicates with the probes, performs all the signal processing, and computes the flow with only a minimal configuration. This makes the method more convenient for more users but complicates the troubleshooting. We can see clearly in this path, the transducer path 1, the transducer path 2. This calculates the distance and time velocity of this acoustic signals, and Doppler velocimeter method applications require the presence of turbulence or particles in which the water flow in opposite the transit time acoustic method, which works best with a steady flow of clear water. Like if the water is here, how much time does it take to reach here, or how much time does it take to cross this path? This gives us the velocity of the water. The principle of acoustic scintillation is that the variation of the refractive index of the water due to turbulence causes random fluctuations in the intensity of acoustic signals traveling along the path. As we can see here, the time signal. Here in the second path, what is the time signal? When this is correlation of this, when this is done, this is the average median time taken. Thermodynamic method. This method uses the principle of energy conservation to determine the efficiency of hydraulic turbine by measuring performance variables such as pressure, temperature, velocity, and level. Unlike the previous methods, it measures the efficiency of the turbine directly and computes the discharge using the generator output and losses. The accuracy of this method increases with the increase of hydraulic energy measured. With the thermodynamic method, efficiency is defined as a ratio of mechanical energy to specific hydraulic energy. Efficiency is given as ratio of mechanical energy to specific hydraulic energy. Both of the specific energies are measured as differences between high pressure section upstream and a low pressure section downstream of the turbine. One is measured during the upstream, like flowing of water upwards, and other is flowing of water downwards. Let us conclude this topic by saying that hydroelectric turbine generator units are equipped with different types of permanent monitoring systems, mainly for maintenance and safety, but not for efficiency management. Several measurement techniques exist to perform the testing, and making the choice depends on the power plant configuration and the instrument capability. Finally, measuring the efficiency of hydraulic power generation is essential for the optimization of its operation, which means more electrical energy and the revenue for the same amount of water. Thank you. This is UDAY SHARMA signing off.